SwayamPrabha. Digital India. Educated India.
In the previous lecture, we have seen the gyroscopic effect on a thin disk, and in that particular case we considered the synchronous world condition. That means, we were trying to aim to find out the critical speed of the system, and we observed that the critical speed increases with the disk effect, that is when the diametral mass moment of inertia of the disk is increasing, then the critical speed also increases. Today we will see another kind of rotor in which the disk will be replaced by a long stick, and we will see that in this particular case the effect of that particular long stick will be opposite to of the thin disk. That means, in this particular case the gyroscopic effect will reduce the critical speed of the system. So, this is the overview of the lecture, in which basically we are dealing with the gyroscopic effect, analysis of cantilever rotor with long stick. Apart from this, we will see is asynchronous valve of a motor disk assembly. In this particular case, we will try to see the valve frequency, and then from there we can able to get the critical speed of the system. And here, when we will be considering the asynchronous valve, we will observe the splitting of the natural frequency of the system due to the gyroscopic couple. So, these are the concepts which we will be covering asynchronous valve. Even for asynchronous valve, we will be having the forward and backward valve frequencies and corresponding critical speeds also. So, let us start the analysis of a long stick which is attached to a cantilever shaft at the free end. So, in this particular case, the stick is attached, this is a long stick, and which is attached to a massless shaft, and in this particular case we are considering the pure rotational motion of the long stick. We are not considering the translation motion at present. So, during whirling, let us say this is the bearing axis, which is Z. So, during whirling, this particular disk is tilting, and its center of gravity remains at the axis of the bearing axis. So, this point is G, and if you see the long stick from this end basically is having circular cross section, to be more precise, and this is the shaft during the whirling. So, this will whirl in this particular configuration. Here also we are considering the synchronous whirl condition. That means, the whirl frequency and the spin speed is same, and we are looking into the condition when they will be same, and that will give us the critical speed of the system. In this, we have not considered any unbalance in this particular rotor. So, for this particular kind of long stick, if we see a small mass dm, let us say this is a small mass dm, because of this motion it will be having a centrifugal force dm omega square, and let us say the axis in this direction is y, and the position of this mass is in, let us say, the coordinate of that is y z. So, that means the centrifugal force will be dm omega square into y, and you can able to see that another mass symmetrically placed opposite to the this previous mass here, this will produce another centrifugal force. The direction is taken care of the negative side of the axis. So, now we can able to see that these two forces, centrifugal force, are making a couple, and the couple direction is counterclockwise direction in this particular figure. So, we can able to see that the tilting of the disc, which is, if we draw the axis of the disc, this is the tilting, that is tilting is phi x about x axis. So, that tilting is becoming more because of this particular moment. So, it is opposite to the previous case. In the thin disc, this kind of moment due to the centrifugal force was trying to reduce this angular displacement, but in this particular case for long stick, this moment is trying to tilt more and more toward the angular displacement direction. So, that means effective stiffness of the system is getting reduced, because more displacement means less stiffness, and we can expect there will be a decrease in the critical speed also, because critical speed is defined as root k by m for this particular case, effective stiffness by m. So, because stiffness is decreasing, so we expect the critical speed will decrease for this particular case. So, now let us analyze this situation. So, in this particular case, let us say the moment in this plane, yz plane, due to one of the small mass dm will be given as the force, which is dm omega square y, and the moment arm of that about the this. So, this distance is basically z, because the coordinate of that particular point is yz. So, this will be the moment produced by this centrifugal force of mass dm. Now, if we want the moment of all such particles of the long stick, we can able to integrate this, and we would get this expression omega square we can able to take common. Now, this particular quantity within the integral is we can able to express that is a product mass moment of inertia, and that can be obtained for this particular long stick. So, let us say for this long stick, along the direction of the along the direction of the axis of the cylinder, let us say is axis 1, and perpendicular to this is axis 2, and let us say I1 and I2 are the mass moment of inertia of this long stick along the two principal axis direction, that is 1 and 2. So, in this particular case, the second figure, that principal axis direction will be inclined, because now this has tilted by phi x direction. Now, we want this product moment of inertia. This will be defined similar to the shear stress concept in the strength of material, that is sin 2 phi x, and because this angular displacement is small, we can approximate sin 2 phi x as 2 phi x, and this will get simplified to I1 minus I2 phi x. For cylindrical shape, this I1 is given as md square by 8, where d is the diameter of the this particular cylinder, d is the diameter, and b is the total length of the cylinder. So, and I2 is given as md square by 16 plus mb square by 12, where b is the length of the stick and d is the diameter. So, once we obtain the moment which is coming from the various particles of the long stick, now we can able to substitute the moment of inertia. Now we can able to substitute the moment of inertia in two principal direction to get the moment. So, the moment we can able to write it as, once we are substituting these two inertia, moment of inertia which we defined earlier, we will get md square by 16 minus mb square by 12. So, I have simplified the expression for after substituting the I1 and I2. So, we can able to see this, we can able to write it as, let us say I am expressing this term within the bracket as id omega square phi x. So, id, the equivalent id for long stick is this much, because if you remember, for thin disk case gyroscopic moment we got exactly same expression id omega square phi x, but id was different for that, but now we are defining the id like this. So, as such, this particular gyroscopic moment is identical to the previous analysis, previous case. In this particular case, while deriving this gyroscopic moment, we considered that the center of gravity of the long stick is at the bearing axis. So, as such, there is no net centrifugal force acting which was there for the thin disk case. But now once we obtain the gyroscopic moment, if we consider the translatory motion also, so as for the thin disk case we will be having the gyroscopic moment, the gyroscopic force Fy as m omega square into y, because in this particular case, sorry, this will be delta. Delta is the linear or translatory motion of the long stick. So, as such, these two expressions are similar as for the thin disk. So, that means whatever the analysis we did in the previous case is valid here also. That means the natural frequency which the critical speed which we obtained in the thin disk case is equally valid here. So, this was the expression we derived in the previous lecture. So, this is still valid here, but only modification will be the definition of the mu. Here mu is similar to the previous one, but id is now defined like this. So, this is the difference. In fact, this particular expression is more general. So, it defined not only for thin disk, also for the long stick, depending upon the relative value of the capital D, the diameter of the stick and the length of the stick. Now, we can able to see that in this particular case, this gyroscopic moment can become 0 if we have some condition, like if we have d square by 16 of minus is equal to mb square by 12. If we have this condition of the long stick, then we will see that ID of that particular system will be 0. So, there will not be any gyroscopic moment. So, you can able to see that the gyroscopic moment becomes 0 if we are having this condition, and if we simplify this, we will get this as B is equal to 0.866 capital D. B is the length of the long stick and D is the diameter. So, if this condition is there, we will be having the 0 gyroscopic moment, and if we have B greater than 0.866 D, you will see that this quantity will be more than this. So, ID will be negative. For this particular case, ID will be negative. So, in this particular case, we have seen that when there is B, which is length of the long stick, is greater than 0.66 into diameter of this particular stick, the mu becomes that is ID becomes negative, and because of that mu, the disk effect also will be negative. So, now we will be plotting the similar graph as we drew for the thin disk case earlier, because the critical speed square and mu, and in this case because mu can be negative also. So, we have two axes. Now, you can able to see in the previous. So, we are plotting this particular expression with respect to mu, and mu we are varying not only from positive direction, but also negative direction. So, earlier we had a curve something like this. It was starting with value 3, and asymptotically it was going toward the value of 12 for omega critical square. Now, if we take the negative value of the mu, we will get a curve which will be asymptotically it will be going toward the 0 omega square critical. So, that means if we recall, this was a point mass, this was a thin disk case, and this was a case in which we had the very large this diametral mass moment of inertia of the disk. Here this will correspond to a long stick, and when we are approaching toward 0 natural frequency, we will see that basically this stick is very long, and for a small disturbance also is having large displacement because of gyroscopic couple is acting toward the angular displacement of the rotor. So, the natural frequency becomes 0 for this particular case. So, you can able to see that whatever we have derived now, this equation represent not only for thin disk case, also for the long stick case. Now, we will see from the non-dimensional critical speed parameter how we can able to get the critical speed. So, earlier we defined the non-dimensional critical speed parameter like this. This is the critical speed, and ml square, L is the length of the shaft. So, we can able to get like if we want the critical speed at this position. So, we have the square of this, and at this position for point mass we have this is equal to 3. So, from this we can able to get the critical speed. Critical speed will be (3 EI by ml square). And if you see the stiffness of the cantilever beam for point mass is basically EI by L. So, basically this is representing as K by M for point mass. For this particular case, we got the value of this is 12. So, if we use here, we will get the critical speed. So, instead of 3, if we use 12, we will get critical speed as the twice of the critical speed which we obtain with point mass. So, you can able to see that the increase in the critical speed due to the disk effect could be as high as twice. In the previous two cases, we considered the synchronous condition. That means, we were trying to find out at what speed the whirl frequency will be equal to the spin speed. So, that means, we were trying to find out the critical speed directly. So, now we will relax that condition, and now we will be considering the whirl frequency which is not equal to the spin speed. That means, we will try to obtain the natural frequency of the system, and in this particular case we will see that the natural frequency of the system depends upon the spin speed of the shaft. So, for this particular case, we will let us say there is a motor and there is a rigid shaft and there is a rigid disc attached to this. So, this whole assembly, motor, the shaft and the disc, is we are assuming is a single unit, and they are rigid body. So, they do not have relative motion among themselves. This is supported on some flexible support. If we see from side, this supported on springs, so that the effective stiffness of the spring against the tilting of the whole assembly, that is Kt. So, in this particular case, we are considering the pure rotational motion, tilting motion of the motor, shaft and disc. So, pure tilting we are considering. That means, the center of this whole assembly is, if this is the center of gravity, is tilting about its center of gravity. So, there is no translatory motion, only tilting motion is there. In this particular case, we can able to see that when this shaft is spinning, which is at high speed, there is a wobbling of the motor shaft assembly, and that will be making a conical shape during the whirling. So, if I draw this is the bearing axis, let us say this is the disc and this motor. So, during whirling it is going in this direction. The whirling frequency is nu, which is not equal to omega, spin speed is the omega. So, in this particular case, we can expect that the shaft and the disc is rotating at a relatively high speed, but whirling will be taking place slowly. So, it will not be that much fast. So, that is why these two are not same. Now, if we consider the angular momentum of this particular disc, so this will be IP, polar mass moment of inertia of the disc, into the spin speed. If we look into this particular angular momentum vector here, so let us say this is the angular momentum IP omega. This is the motion of the disc. So, this angular momentum will be moving along with the disc in the whirling direction. So, let us say whirling direction is counterclockwise when we are looking from the right side. This is the frequency of the whirl. So, and tilting of this we are giving, let us say, phi x angle. So, this angle is phi x. So, let us say at the apex this disk is there at time t is equal to 0, and after some time it is reaching, let us say this point is B. So, it will reach somewhere here because folding direction is counterclockwise direction. So, after some time t, let us say this point is C. This point is C, and the angular momentum will occupy this position. So, B to C is the change in angular momentum. This B to C is nothing but change in the angular momentum. Now, this particular angle, which is connecting the center of rotation of the disk, this is on the bearing axis, let us say point A. So, this angle that is CAB, that will be nothing but nu into delta t time. So, delta t time, because this angle is because the frequency of hole is nu and time taken from moving from B to C is delta t. So, this will be the angle nu dt, this BAC will be the angle this much. Let us say the change in the angular momentum, we are writing with respect to the angular momentum. So, basically in the previous figure, change in angular momentum was BC and the angular momentum was OB. So, OB, let us go to the figure. O is this one. So, from here to B is the angular momentum and BC is the change in angular momentum. So, this can be written as BC by AB and AB by OB. Now, BC by AB is in the previous figure, BC by AB is nothing but this particular angle nu dt. So, this is nu dt, and AB by OB in previous figure, AB by OB is the phi x angle, phi x angle. So, this expression we can able to write as d change in angular momentum with respect to time is equal to IP omega nu phi x. So, rate of change of angular momentum is nothing but the moment, gyroscopic moment. So, you can able to see this is the gyroscopic moment which is producing because of the whirling and spinning of the shaft. So, this is the gyroscopic moment. And the direction of this will be in the direction of the BC. So, BC direction is, that is outside the screen, the vector will be toward the outside the screen, B to C. So, this particular gyroscopic moment will, the disc will experience from the motor frame. So, the reaction of that onto the motor frame will be opposite. That means, in this particular figure, it will be from C to B, that will be into the screen direction. So, according to the right hand rule, it will be, if we see into the screen, that will be clockwise direction. So, onto the motor frame, it will be acting in clockwise direction. So, if we see the this particular figure, when moment is acting in the clockwise direction, or this figure, that moment will try to reduce this particular angle. That means, it is trying to reduce the tilting of the this particular motor shaft assembly, and because of that basically the effective stiffness is increasing. Apart from this particular moment, the moment due to the support, and the support, the effective stiffness is kT, that will also be acting opposite to the angular displacement. So, we will be having basically total moment not only from the support spring, but also from the gyroscopic moment as this much. So, the stiffness into the angular displacement will give the support displace moment, and this is the gyroscopic moment. Now, this is the moment. So, the stiffness will be moment divided by this angle. So, that means the effective stiffness on the system will be kT plus minus IP omega square nu, and the world frequency will be the stiffness, effective stiffness, this particular stiffness kT plus minus IP omega nu divided by ID, because the tilting is about diameter. So, the stiffness divided by the diametral mass moment of inertia, and that is actually the world frequency square. So, we know that the natural frequency square is stiffness by mass. So, this particular equation will give us a quadratic equation in terms of nu. This equation will give a quadratic equation in terms of nu, and this can be solved in closed form. So, this will give us the world frequency expression plus kT by ID. So, this is the world frequency equation, and you will see that this world frequency, which is natural frequency of the system, now depends upon the spin speed of the shaft. And in this particular case, basically 4 roots are visible because there are plus minus signs, but if you take the negative outside the square root, we will get 2 frequency which both will be negative, because negative frequency is having no meaning. So, we can able to ignore that, and basically those 2 negative values of the frequency, exactly same value will be getting when we are considering the positive sign. So, basically the negative sign is we are omitting here. So, now we have this equation, and this can be simplified by defining non-dimensional parameter. Let us say nu bar, I am defining as this world frequency ratio as ID by kT, and spin speed ratio I am defining as kT into ID. Now, with these 2 non-dimensional terms, if we use in this equation will get simplified to omega bar plus omega bar square plus 1. So, this is a simple equation. Now, this we can able to plot So, this equation I am plotting it with respect to nu and the spin speed ratio. So, at omega is equal to 0, we expect there will be a single value. If we put omega is equal to 0, basically we are getting 1 only. So, that is this point 1, and as we will increase the omega bar, we will find that there will be two values. One will be increasing in this direction and another will be decreasing. So, this is basically the splitting of the natural frequency is taking place, splitting of frequency is taking place, and this particular frequency is corresponding to the forward whirl. That means the whirl direction will be same as the spin speed. This is the backward whirl, in which the frequency of whirl will be opposite to the spin speed. And if we want the critical speed, obviously in this particular expression, critical speed, for that we need to put nu is equal to omega bar, that is the critical speed condition. Sorry, this condition, not the bars, because we have defined these two differently. So, we need to go to this expression and we need to put nu is equal to omega, and we need to solve for omega, that will be omega critical. Nu is equal to omega, here we will able to get the critical speed. We will be getting two values of this, first and second, and the expression will be kT divided by ID minus plus IP. So, this minus is corresponding to the forward whirl and plus is corresponding to the backward whirl, because when the denominator is minus, obviously this quantity will be smaller and we will be getting the higher critical speed, that will be corresponding to the forward whirl natural frequency, and when it is positive, we will be getting denominator higher as compared to previous one. So, we will be getting critical speed lesser, that will be corresponding to the backward whirl critical speed. So, we have seen that how the whirl frequency depends upon the spin speed of the shaft when we are considering the asynchronous whirl. And now, through one example, we will see how a rigid rotor which is supported on a spring can have a gyroscopic effect and how the whirl frequency changes for that case. So, we have a long symmetric rotor which is supported at ends by two identical bearings, and these bearings will be modeling by only direct stiffness terms. The shaft is having diameter of 0.2 meter, length 1 meter, and material properties are given here. We have neglected the damping in this particular case. We are considering pure tilting motion of this particular rotor, and gyroscopic couple we are including in this. So, we want the whirl frequency at one particular RPM, and also we can able to calculate the critical speed, because whirl frequency is changing with speed and we need to track at what speed these frequencies are equal, and that is nothing but the critical speed. So, for a given parameter we can able to calculate the rotor polar moment of inertia, its diametral moment of inertia, and this is the spin speed at which we are interested to obtain the whirl frequency. So, in this particular case, we have considered the pure tilting motion of this particular shaft. Now, because it is tilting about its center of gravity, the tilting, let us say we are considering in one of the plane phi x, and because of this the extension of the spring which are here will be this much, because this is the half L and this angle. So, this will be the extension of the spring here. So, this will exert this particular force from the spring in the downward direction, and this is getting same amount of compression. So, here we will be having a spring force which will be upward. Now, these forces are making couple. So, basically they are providing a couple and this or moment, and that moment will be nothing but this force value into the length of the shaft. So, this is the moment which is acting, and if we divide this moment by the angular displacement, we will get the effective stiffness of the support or the rotational stiffness of the support. Moment divided by angular displacement will give us the effective support stiffness against the rotation. And the expression which we derive for present case, the motor shaft disc assembly, this particular case is identical to that one. So, whatever the we had expressions for the Hall frequency will be valid here. And in this particular case, if we obtain the effective stiffness kT will be this much. If we substitute the previous moment of inertia and spin speed and this effective stiffness in this expression, we will get the forward Hall frequency as 187.67 radians per second, this forward Hall frequency, and backward Hall frequency which will be less than this radians per second, 126.67 radians per second. This is backward Hall frequency. So, you can able to see that the spin speed was 1047 radians per second, but Hall frequencies are these. So, obviously, we are well above the critical speed. If we want the critical speed, we can able to use the expression which we derived earlier, that is effective stiffness divided by ID plus minus plus IP. So, this will give us the two critical speeds corresponding to forward Hall. We will be getting critical speed is 158.88 radians per second, and second one is 149.88. So, this is corresponding to forward Hall critical speed and this is backward Hall frequency. Now, we want to compare the critical speed of the system when there is no gyroscopic couple. So, for that particular case, we will be having the critical speed or the natural frequency in that particular case will be same as the critical speed, will be K effective divided by ID. So, if we substitute the value in this, we will get 154.18 radians per second. So, we expect this to be in between the forward Hall and backward Hall, because as we have seen in the previous case, when we varied the frequency with the spin speed at 0 speed, when there is no gyroscopic couple, this was having single value. So, that is corresponding to this one, and as we are increasing the speed, let us say here we are getting two values. Similarly, we can able to get for other speeds another two values. If we join them, we will get the world frequency variation for forward and backward world with respect to spin speed. So, in the present lecture, we have considered two cases. One was the pure rotation of the a long stick, and another case we considered a whole assembly of the motor and shaft disc for pure rotation, and in this particular case we considered the asynchronous world. That means we considered the whirling frequency and the spin speed different, and we found that because of this the whirl frequency is getting split in two, and correspondingly we have forward whirl and backward whirl, and in this particular case corresponding critical speeds also we had two in numbers corresponding to the forward critical speed and backward critical speed. So, in this particular lecture we have seen one interesting phenomena, the splitting of the whirl frequency and the forward whirl and backward whirl of this critical speeds.